Hello, everyone. Welcome to the session of the 2022 P4 workshop. My name is Carmelo Cascone, and I'm a software engineer at Intel. And I'm also a SD Fabric project technical steering team member at ONF.
Hello, everyone. I'm Charles Chan, and I'm also a software engineer at Intel and a member of the SD Fabric technical steering team. So, Carmelo, what are we going to talk about today?
Well, the introduction of the P4 language has generated an explosion of ideas for ways to make networks better, especially for data center networks. But the path to go from a P4 idea to developing something can be deployed on a real data center network is not easy. To do that, we need to start thinking about writing the control plane, how to do routing, how to react to failures, how to deploy, monitor, and update the software stack, etc. So clearly, there's much more that goes into building a network other than writing a P4 program. So today we will discuss how to make this process easier with SD Fabric. If you're a P4 developer, it's helpful to think at SD Fabric as a platform to realize your P4 ideas. So SD Fabric is a data center fabric entirely defined by software, from the data plane to the control plane. Because it's software and it's open source, you can extend it to try out your ideas and potentially deploy them on a real network. In a nutshell, SD Fabric provides you with three fundamental building blocks. There's a P4 program that you can use as a starting point. This program provides basic forwarding capabilities and also advanced ones like 5G UPF, INT, slicing, and much more. It provides a production-grade SDN control plane with high-level APIs that make it easier to build new control applications for your P4 idea, while at the same time providing built-in applications that you can reuse to realize common features instead of implementing them from scratch. Finally, we provide integration with cloud native and CI/CD tools to make it easier to deploy and monitor the full stack in production. So what is this tutorial about? We created this tutorial for you to quickly get started with SD Fabric. So the goal is for you to learn a few things. We want you to learn about the architecture. We want you to be able to deep dive into existing features from basic ones to more advanced ones. And also we want you to get some hands-on experience. And for this, we created hands-on exercises that are based on an emulated environment that you can run at home in your laptop. So in this tutorial, we're going to use the SD Fabric release version 1.1. This is this release and the whole SD Fabric project is hosted by the Open Networking Foundation, and it's released under the Apache 2.0 open source license. So you can go there, download it, and use it today. If you want more details on how to use SD Fabric, with real switches, we suggest you to go and check our documentation website. If you need if you want to stay in touch, or if you need help with exercises or questions in general, then you can visit this website and you can find their links to our mailing list, Slack channel, wiki, etc. Okay, so today's session is divided in three parts. We will start with a high-level overview of the project, touching on the motivation, architecture, and the current use cases. Then we will move into a deep dive of the various features, with each part followed by an hands-on lab. Part 2 is about learning how to configure the basic forwarding inside the fabric, while part 3 is about showing an example of how you can use P4 to develop innovative features. So we will talk about the design of our P4-based user plane functions, and we will show how to use it. And that's all for today, but we plan on making more sessions available in the near future. So make sure to visit our GitHub repo and subscribe for updates. In this repo, you will find a link to the slides as well as code for the hands-on lab. Okay, so I think it's time to get started. So Charles, do you want us to give us an overview of the project?
Okay, thank you, Carmelo, for giving us the overview introduction. So now I'm going to start the first part of the tutorial, which is to talk a little bit more about the SD Fabric project. So just quickly setting up the context, there is a broad agreement now that we're moving towards to the distributed cloud architecture. We're in an era of everybody adopting hyperscale clouds, but the cloud is also moving towards the edge. And we're seeing different forms of edges, including telco edge, enterprise edge, and some colo edge. Hyperscale cloud, despite being extremely flexible and offering huge capacity, are typically challenged for higher latency and expensive bandwidth. Edge cloud, on the other hand, offer benefits such as lower latency with much smaller scale at much lower cost. Another industry trend is that 5G is now becoming the last mile link to the end devices. So the challenge we've been facing is the ability to connect the explosion number of devices shown on the left towards the various cloud resources on the right. There are different forms of compute and networking resources of different sizes inside each cloud, but there are lots of common requirements and challenges across these data centers. We're also seeing numerous of new use cases being introduced that include multi-cloud applications, IoT, and as a result of IoT, an explosive amount of devices, 5G, AI, and machine learning. So we talk about the potential of multi-cloud connected edge, and clearly the data centers need to be evolved to support those emerging use cases. And we're seeing a couple of new characteristics or requirements coming up. First thing is that the line between the servers and networking are blurring. We're seeing a rapidly increasing data demands, and we need to build a solution in a more flexible and cohesive way, and hence you're seeing the notion here of viewing the solution as a programmable cluster of computing capacities. We're also, of course, moving towards a developer-focused world. So all these need to be developer optimized. That means deeply programmable, end-to-end, and throughout each of the components. And we must be able to easily distribute the workload to various resources, including CPU, GPU, IPU, or switches. And all these need to be accessible easily through a well-defined API. The data center needs to be cloud managed, meaning that it has to be deployed, managed, and monitored by cloud platforms. It needs to provide easy access to gauges and dials for application visibility and control. We also now have to consider network traffic end-to-end, including not only the underlay fabrics switches, but also the container network, software switches, and IPUs on the host. Finally, all these components need to be centrally orchestrated. We believe doing so can bring a huge benefit in terms of having global visibility and being able to optimize. So this page shows a little bit of history about how the open source networking fabric built from Honest that evolves. So back in 2015, that's when we started Project Atrium. And by that time, we were just trying to demonstrate the feasibility of SDN and OpenFlow solutions by providing a complete software stack that includes applications, controller, switch operating system, SDK, and ASIC. And that project soon evolved into the network infrastructure for Cord, our central office re-architected as a data center project, which mainly focused on telco data center and use cases. And by that time, we introduced a lot of new features. And then in 2017, that's when we first named the project Trellis, and that's when we start collaborating with Comcast. During that time, we've done a lot of platform hardening, and we also scaled up the system to meet the Comcast requirement. Between 2018 and 19, we've done a series of field trials and production deployment with Comcast, and those are based on Broadcom OFDPA fixed function ASICs. And by that time, we also start exploring and trying to support programmable ASIC. We're trying to adopt a key design principle that we use the Flow Objective API, which is a pipeline agnostic API, to build our control applications, such that we can use exactly the same application to control both OFDPA switches and the programmable ASICs. So in 2020, that's when we started the project called SD Fabric. The main difference of SD Fabric compared to Trellis is that now we are fully integrating the fully programmable, fully visible data plane. And this is also when we start the Ether project, and that's our private 5G edge use cases, and that's our primary driving use cases for SD Fabric. So SD Fabric is an open source cloud managed fabric solution. The key hardware component is the leaf-spine fabric, to which we connect servers, various access devices like Wi-Fi, 5G, and broadband access, and the internet. And there are three key features of the SD Fabric. So first, SD Fabric has a fully programmable and visible data plane. It is powered by Intel Tofino chips and can potentially be expanded to cover IPUs in the future. The programmability enable network function offloading, so we can easily implement SASE, tunnel termination, firewall as a service, and 5G UPF. The visibility also allows us to implement embed network telemetry, or INT, and use that to further enable closed-loop control. The flexibility also makes resource optimization per use case possible. Second, it benefits all the advantage that SDN has. Everything is now centrally managed, so we avoid a lot of overhead caused by distributed network protocols. It is also easy to achieve global optimization with SDN approach. We offer redundancies on both control and data plane, one big router abstractions, and a lot of common features such as bridging, ECMP routing, echo table, LDP, and DHCP. Last but not least, SD Fabric is completely cloud managed. This allows us to implement automatic provisioning, lifecycle management, failure recovery for all the servers and switches. We can also manage multiple sites with the state-of-the-art cloud-native CI/CD monitoring, telemetry, logging, and alert system. Our approach uses Open Networking Linux and Stratum as the switch operating system and agent, and the SDN controller communicate with the switch via P4 runtime and GNMI. Stratum supports fully customizable P4 pipeline and can be configured, managed, and monitored by SD Fabric Cloud Management Platform. We will discuss more in the next couple of slides. An alternative approach is to use Sonic and pins. In this case, SDN controller are also communicate with the switch via P4 runtime and GNMI, but it will require some custom P4 table support in Sonic to unleash the full potential of programmable data plane, which is yet to be implemented, but this is on our roadmap. So we have a production-grade open source SDN control plane. It is scalable, redundant, and support various southbound protocols such as P4 runtime and GNMI, and that's all we need to program the switches. We have built a set of Fabric apps, which can be sorted into 3 categories. The first is the forwarding features that include L2 bridging, L3 ECMP routing, ACL, multicast, DHCP relay, and dual homing. The second category is the 4G, 5G user plan that include GTPU tunnel termination and QoS support. The third category is the INT watch list that allow us to define what flows we want to monitor and collect the network telemetry. Note that even we choose to go with the full SDN approach so far, the current architecture doesn't prevent us from supporting a hybrid mode. That is, we can have legacy features controlled by a switch agent like Sonic, and that SDN control the new features. After all, there are already a lot of features supported by Sonic, and it doesn't make too much sense to reinvent the wheels. This page is going to illustrate the cloud-native tools we use to manage and operate SD Fabric, and that includes a set of CI/CD tool for provision and configuration, a matrix collector and time series database for monitoring, a log collector and a full text search engine for logging and alert, an INT collector, and the analytic engine, which is still a work in progress for the network telemetry. It is worth noting that all these features are powered by state-of-the-art cloud-native solutions backed by a tremendous open source ecosystem. We adopt modern DevOps and GitOps approaches and bring all the operational information into a single pane of glass. SD Fabric is also scalable and redundant. It supports various scales, starting from the smallest one, the single switch. That is the one that comes with lowest the cost with no redundancy. And then we can scale it up by pairing the switch with another one to create a leaf pair. That will give us some redundancy over leaf and host failure. We can further scale it up to a full leaf spine fabric, and that will give us redundancy over leaf, spine, link, and host failure. So larger the network grows, more redundancy and capacity it has. SD Fabric offers that flexibility and scalability. At its largest scale, we can have redundancy all over the places. So here is the one main key takeaway. SD Fabric provides a solid foundation for developers to take advantage of programmable data planes to deliver innovative features. So next, I'm going to head it over to Carmelo, where he'll talk about some use cases that we build on top of SD Fabric.
Okay, thanks, Lars. Right, so the main use case right now for SD Fabric, it's Ether. So Ether is ONF's private 5G connected edge solution. Here, I want for you to get a sense of the building blocks that we can reuse, to build your own fabric with your own P4 idea. So in Ether, the goal is to provide connectivity between 5G connected devices on the left and edge applications running on the servers. The focus is mostly on Industry 4.0 scenarios where we want to connect mostly machines or sensors to support automation use cases. So there is a strong requirement on low latency and high bandwidth communication. So how do we do this? Like every 5G network, we need a user plane function to terminate and perform other functions on GPU tunnels. And so to achieve this guaranteed low latency and high bandwidth, what we did is we fully offloaded the UPF data path pipeline into the switch. Okay. Now, because the switching ASIC has limited memory, we also implemented a DPDK-based UPF to achieve horizontal scalability. But you might start to notice that this is becoming a complex topology, and you might be wondering, how do we integrate all of this with a 5G core control plane? So does the 5G core need to manage all this complexity? Well, the answer is no, and this is where SDN becomes really useful. So we built an app that we call here the UPF app that essentially abstracts the whole network, the whole fabric as a one big UPF device to the 5G core. So this app implements a standard 3GPP interface called PFCP. The 5G core believes it's controlling a single device, while the application internally takes care of inserting rules into the different UPF functions across the fabric and handle the forwarding between them. So next, to provide performance guarantees, we support slicing. So here the idea is to partition the fabric into end-to-end slices with strong isolation and QoS guarantees. Like in the previous case, here we also built anonymous applications that provides APIs to the upper layers to be able to create slices and map traffic into slices. Then internally, the application takes care of doing things like configuring queues, configuring schedulers, and other features of Tofino's traffic manager. So today we enforce isolation and QoS on the switch only, but there's a plan to extend this also into the NIC and the host. Okay, so last, since we are supporting mission critical applications, we need a way to verify that we are actually meeting the application service level agreements. And so for this reason, we added support for INT, so in-band network telemetry. So switches have, the switch pipeline has been extended to add support for generating INT reports that allows us to track things like the path, drops, the latency, or if there is congestion, we can quickly find that out. We also have an applications running on top of ONOS that allows the upper layers to manage things like the INT watch list, so which traffic we want to monitor, and configure things like thresholds for anomaly detection. Also in this case, today we have an implementation for INT that runs on the switch. We also have a prototype of INT support on the host that is based on eBPF, and we have plans to extend this also on the NIC. Here the goal is to be able to observe packets as they go from one container to another, or from as they enter the fabric from the base stations to the containers running the edge applications. Okay, so finally, what we do with the INT reports is we feed them into our INT collector, which is Intel Deep Insight, which is a commercial INT analytics platform, and we use this to realize a closed loop control. So Intel Deep Insight receives all the INT reports and correlates them with topology information, and by doing that, it generates more meaningful, high-level per-flow statistics and anomalies. This information from Deep Insight, the plan here is to build a verification engine that can consume all this information together with network state coming from ONO. So think about the device state, link state, switch counters, etc., as well as configuration state. So think about the subscriber configuration, which applications are enabled or not. And the idea for the verification engine is to crunch all the data and do two things. So when possible, realize what we call self-adaptation and healing. So this is where we actually close the loop. So think about for example, the idea of like tuning QoS as soon as we realize application performance issues, or being able to shut down malicious traffic as soon as we detect that. When self-adaptation is not possible, the idea is to use all this information to be able to generate what we call smart alarms that allows the operator to improve troubleshooting time. So the idea is to provide information not only on the issue itself, but also on what is the potential root cause. Okay, so that's all for part one. To recap, we introduced the motivation to SD Fabric, the architecture, and the main driving use case. So next up is Charles with part two, where he's going to talk about how to configure SD Fabric to do basic forwarding.